Hello, friends. Welcome back. I hope everyone had a restful spring break and is safe and healthy and being responsible with all of our social distancing mandates. Taping this lecture at home from my daughter's bedroom because it's the only room in the house with a nice desk in it. My dog is in the room. Maybe I'll introduce him later. Snoop. There he is. That's Snoopy. I want to start by reiterating the point I made in the announcement that I put on Canvas about the class moving forward. Obviously, things are going to be very different. I've never taught like this before. I certainly don't know everything about online learning. Bear with me. I put some time into trying to make this as seamless as possible, but I'm sure there will be technical glitches that come up. I'm also terrible on camera. Apologies in advance. On my end, I want to do everything I can to make this class as low stress as possible for you. I'm going to be taping these lectures in 10 to 15 minute chunks and posting them to Canvas. You can watch them on your own schedule. Homework will still be due every week, but I will be giving a lot more tries on every question, and I'll be posting videos explaining some of the trickier problems as we go. Our first exam is this week. It will be the same length and difficulty as previous exams, but will be administered on Canvas. You can take the exam anytime between Thursday of this week and Sunday. Once you start the exam, you'll have a 75-minute window in which to complete it. But as I have no way of enforcing any restrictions on use of outside material, I'm not even going to try. You're welcome to use your book, your notes, the internet, really anything other than other people. Please do the exam on your own and don't post anything or talk to anyone about it until Monday when everyone has taken it. I'm guessing the average on this exam will be much higher than the previous one, and I'm okay with that. There is an exam 2 prep page on Canvas that you should take a look at that does have a practice exam posted. You should probably do some studying and looking over the previous exam. But again, I don't want anyone stressing too much about this. I plan to hold office hours during our normal class time at 10 a.m. on Tuesdays and Thursdays. I'm going to try to do this with Blackboard Collaborate, but if it doesn't work well, I may try something different. We'll see how it goes. I think that's it for announcements. I probably won't do an APOD with every video, but today's happens to be very appropriate for the class topic for today. So here it is. Where is it? Here it is. Here it is. I hope you're seeing that now. What are we looking at here? It is space, but it's not a particularly crowded region of space. So lots of things going on in this picture. You can see at the top is the Pleiades cluster. We've looked at this before. This is an open cluster, a nearby, lots of young stars. It's about 100 million years old. But this is a huge view of the sky. And you can see one of the lessons from today's class is space, although you've been told that it's completely empty, is not completely empty. There's stuff out there. It is not a perfect vacuum. And it's not even uniform. There are regions that are very patchy. There are regions that are very dark. There's regions that you can see through and there isn't much of anything at all. There is stuff out there. This stuff we call the interstellar medium, and it is in fact the topic of today's lecture. So let's start with a review question. You remember all the way back to last Thursday, the Thursday before break. We were talking about clusters of stars, and we were talking about particularly how you could use clusters to determine the ages of stars and the distances to stars. So today's review question is, hopefully you're seeing the review question now. Today's review question is, which of these clusters is younger? We've got 2 clusters here, A and B. Hopefully you can see my laser pointer now. And these lines are the patterns that the stars make on the HR diagram. I want to point out that this is apparent magnitude and this is temperature. It's a normal HR diagram as usual, except this is apparent magnitude and not absolute magnitude. That's important. And temperature as usual on HR diagram is increasing towards the left in this direction. So which of these clusters is younger? we're not doing any top hat. This is all asynchronous. But if you like to pause and think about this, we'll come back and talk about it in a second. Okay, pause over. So which of these clusters is younger and how can you tell? Well, as we know, the upper left of the main sequence, let's look at cluster A. These are the very massive stars, the hot stars, the very bright stars, and these are the very low mass, cool, dim stars. And we know that for a cluster like this, these stars up here at the top will lead very short lives. The fact that these stars are still on the main sequence says that this is a fairly young cluster. You can see what happens for cluster A and B. Basically, the redder the stars are at the turnoff point. So here's a turnoff point for cluster A, the turnoff point for cluster B rather. Cluster A, we don't even really see a turnoff point. Cluster A must be the younger cluster because these stars, which lead very short lives, are still on the main sequence. And these stars are all off the main sequence. The equivalent stars up here on cluster B are all off the main sequence. And so B must be a much older cluster. A must be the younger cluster. And you can tell just by the temperature, the color of the main sequence turnoff. Now, if this were an absolute magnitude scale, well, let's ask the next question and then we'll talk about that. Review question number 2, this is a 2-part review question. Which of these clusters is farther away, A or B? Same 2 clusters. I'll pause and let you think about that. You can pause the video if you'd like. Okay, coming back. Which of these is further away? Now, here's the thing to remember. This is apparent magnitude. So this is how bright these stars appear to be. And again, bright is on top and faint is on the bottom. These stars on the main sequence, all the stars in a particular cluster, let's say A, have the same distance. That's what a cluster is. It's a region of space that has it's a region, a group of stars that are all in the same region in space. And so they all have about the same distance. And the same is true of cluster B. These 2 stars have the same temperature, right? And they're on the main sequence. These 2 stars should be identical between cluster A and cluster B. They should have the same properties. They should have the same mass. They should have the same radius, roughly. They should have the same luminosity. And that's the critical one that's important here. These 2 stars should be exactly the same intrinsic brightness. The fact that the star in cluster B looks brighter to us says that it must be the closer cluster to us. So really, it's just whichever star appears brighter, whichever main sequence is higher, those stars must be closer to us. So B must be the closer cluster and A must be the cluster that's further away. Okay, that's confusing. If you have questions, you can send me an email or watch this video again. But that's how you can tell immediately by looking at these clusters, which is older and which is further away. Where these guys show up on an apparent magnitude versus color diagram will tell you both of those things. Okay, let's get to it. We have finished talking about what we know about stars, and we need to think about now how stars are basically stellar evolution. We're going into how stars evolve and how we know how they evolve. But first, we need to briefly talk about chapter 20. I think it's a fairly boring chapter, and I think I'm going to tell you everything you need to know about chapter 20 in 2 slides. So here we go. You ready? The interstellar medium, the gas and dust in space. Basically, APOD told you everything you needed to know. Here it is. Here's another less good picture of the interstellar medium. The thing that you've been told that space is empty is a lie. There is lots of stuff up there. It is a good vacuum, but it's not a perfect vacuum. There is stuff out there. As you know from homework this week, there are something like from a few to a few thousand atoms per cubic centimeter, which is a very good vacuum, much better than what we're dealing with here on Earth. But it is not empty. And in fact, there are regions of space that look rather crowded. It's also clumpy. It's not a perfectly uniform thing, the interstellar medium, and that's good for forming stars, as we will see. So here's another diagram showing the clumpiness. This is the Andromeda galaxy, which you can see there's lots of stars in this picture. Many of these are foreground stars, but some of these very things are actually in the Andromeda galaxy itself. But I want you to focus on not the stars, but the region, the interstellar medium, the region between the stars. And here you can see different components of a galaxy, the Milky Way included, as seen in the Andromeda Galaxy. So let's look at these and think about them. You can see ionized H2 regions. These are these pink regions. These are regions where the nearby stars have heated up the gas and caused it to glow. H2, the 2 here is a Roman numeral 2 referring to ionized hydrogen. H1 is neutral hydrogen. H2 is ionized hydrogen, not to be confused with the superscript 2 that refers to whether it's hydrogen or, say, deuterium. This Roman numeral 1 or 2 refers to ionized gas. And the ionized gas has been heated up by something, and that makes it glow in these characteristic pink regions. But that's a fairly small region, as you can see, of the Andromeda Galaxy's interstellar medium. These dark clouds that you see sort of forming in the spiral arms of the Andromeda Galaxy are molecular clouds. These are the coolest regions and densest regions of the interstellar medium, and they become so dense that they even block out stellar light behind them. And you can see this is also very clumpy. There aren't many ionized regions. There's a few more molecular clouds, but that still doesn't make up the majority of the interstellar medium of the Andromeda Galaxy. Most of this is just diffuse neutral hydrogen. And that makes up the most of the interstellar medium, both of the Milky Way and of the Andromeda Galaxy. Okay. That is the end of chapter 20. Hope you liked it. I will end this first video there, and we will continue with chapter 21 in the next video.